We present rotated, general in-hand object rotation with vision and touch. In-hand manipulation happens every day in our life. When we use tools such as the hammer on the top left, the way we grasp it might be different from the way we use it. When we want to install light bulbs, use screwdrivers, utensils, and do handwriting, we constantly use our fine manipulation skills with our fingers. Our research aims to enable robot hands to have the same level of dexterity, using an integration of multimodality sensing and machine learning techniques. Previous work shows, one can train a policy with only proprioception in simulation, and transfer it to the real world. It can rotate a large set of objects. However, the rotation is limited to z-axis. In this work, we extend previous work to enable the robot hand to rotate objects over multiple axes. For example, it can rotate objects over 6 principal axes. And it is still able to generalize to different objects. The key of this project is using a stream of vision, touch, and proprioception to continuously infer object shape and physical properties during deployment. This information will be sent to a learned policy to adaptively rotate the objects. Here is a small gallery of our results. We show rotation axis on the top, and demonstrate many different objects we tried to rotate. Here is an overview of our method. We split the training into 2 stages, both happen in simulation. In the high level, the idea is to first train an oracle policy. It's called oracle because it has access to all the ground truth information such as object pose and shape, which we called privileged information. The policy will have a very high performance, but we cannot use it in the real world. Then we distill it to a sensoromotor policy by trying to imitate the oracle policy. We need to design the input space so that the sim-to-real gap is as small as possible. More specifically, our privileged information contains object pose, physical parameters, and ground truth object shapes. We feed them into a neural network, called privileged encoder, to produce a feature representation. We call it extrinsics, denoted as ZT. For object shape, we use a point net to encode object point cloud to a vector. This vector is concatenated with other privileged informations to feed into the privileged encoder. We optimize this policy using reinforcement learning, with respect to a few reward and penalties terms. It tries to maximize rotation reward, defined as the product of angular velocity and desired rotation axis. It also minimizes the undesired rotation quantity, defined by the rotation component other than the desired rotation axis. In addition, there are a few energy and smoothness terms to make the policy operate smoothly and safely. This policy performs very well in simulation. However, if we want to deploy it in the real world, we need to consider ways to infer the extrinsic information in the real world. In this paper, we demonstrate how to use vision and touch to do that. The high-level idea is to use a stream of multimodal observation and feed them into a temporal transformer to predict ZT. Now our goal is to find an observation space that we can easily get both in sim and real world. For vision, we use object depth as an abstraction of images. In simulation, the simulator provides us the object depth. In the real world, we use Intel RealSense and then run segment anything on the image. Things are a bit trickier for tactile sensing. We use an image-based omnidirectional sensor as our tactile information. But that is very hard to simulate accurately. Therefore we use a low-dimensional representation of touch, more specifically, a discretized 2D contact locations. Here is a visualization of how we use tactile information. When the object contact the fingertip from different directions, the sensor will deform in different directions. And then we can calculate the displacement between the current image and original background image to get the direction of contact. Finally, we discretize it to an 8-dimensional one-hot vector. We also conduct comprehensive experiments. The first question we want to ask is, does the object shape in our oracle policy help training? We compare oracle policy trained with and without the point cloud shape representation. And we find oracle policy with shape input significantly outperforms its plane counterpart. To get more insights, we compare the relative reward improvements on different objects. We find it particularly helpful on challenging objects. Next, we study how to close the gap between sensoromotor policy and the oracle policy. Starting with only proprioception input, it is much worse than the oracle policy. When we add vision, it improves a lot. Similarly, when we add touch, it is also much better than using proprioception only. When we add vision and touch at the same time, it gets further improvements, almost match the Oracle policy. We observed a similar phenomenon for stability metric, it measured normalized time before falling. The trend is the same for all three axes. Similarly, we find it improves mostly in challenging objects. Then, we run evaluation on 15 challenging and unseen objects during training. We find that using shape information for Oracle policy, or using visuotactile, can significantly help out of distribution generalization. Finally, we are interested in if our policy really learns object geometry as a feature. To study this, after we training the policy, we collect a dataset of the extrinsics for different objects. We collect 4 datasets for different policies: policy without point cloud, Oracle policy with point cloud, a proprioception-only policy, our visuotactile policy. We try to train a decoder from the extrinsics to predict object 3D shapes. We find that for stage 1 policy, even when there is no reconstruction loss during policy training, it still recovers the object shape, meaning that this information is useful for policy training and has not been discarded. However, if we don't have shape representation, the policy can only guess every object is a cube or sphere-like object. For stage 2 policies, visuotactile policy can successfully recover object shape, meaning that using a history of depth image and low-dimensional tactile embedding can successfully learn the representation of object shape, while only using proprioception cannot. Thanks for watching this video. To learn more of our project, feel free to check our website or contact us.